Yeah.
Are you taking a test for her? No, one. Oh, okay. What? You seem really good. I don't think so. I'm just trying to bad to get her.
I'll continue on with capillaries. Okay, the capillaries. We get all the bullet points up here. We're down to one layer. One layer. One layer is just a TI. Maybe there's a basement membrane, but just one layer. They're just an endothelium, basically. And some properties of capillaries, even though they're the smallest, they only have one cell layer thick with the basement membrane. Well, that's for more efficient exchange. Okay, it's hard to exchange across a thick surface. So it's good just to have one layer, and they're only 1 millimeter in length. So the diameter is microscopic, 8 to 10 microns in diameter. And then, so they exist in beds, as I said before. Capillary beds, they provide a lot of surface area for exchange. Now, surface area, basically I just say cm squared, right? Multiply length times width, that's area. Well, anyways, all that surface area, because there's so many capillary beds, there's a lot of surface area for gas exchange and other things. The idea of rouleau, R-O-U-L-E-A-U, X, R-O-U-L-E-A-U-X. This is something we see in the red blood cells as they flow through capillaries. The diameter of a capillary can only allow one red blood cell to pass at a time. So they kind of have to line up single file, the red blood cells, to go through capillaries. So rouleau is the RBCs stacking on one each other. So that they can file through. Here's a picture of that. So this is muscle bed, but the capillaries file through single file like a stack of pancakes. Because let's remember that red blood cells are not round cells like beach balls, they're flattened in the middle. Like that. We call it a biconcave shaped cell as you look at it from the side. Concave means curves in. If you curve in on both sides, that's biconcave. So this allows for more efficient stacking. Like a stack of pancakes, I guess. Okay, so anyways, there are different kinds of capillaries. If the job of capillaries is for exchange, the question is, how much exchange do you want to allow? All capillaries exchange. Some are not so leaky, some are very leaky. So we have to define continuous fenestrated sinusoidal capillaries. Continuous capillaries, the endothelium is more or less continuous. There's not a lot of gaps and spaces in between cells. So they limit the exchange. They're not so leaky. A continuous endothelium. So for example, skin, muscle, are good places where you want to limit the exchange. For example, skin is a membrane barrier to protect against infection, so that kind of helps keep infection out, to have capillaries that are not so leaky. In muscle, when you work out, you build up lactic acid, which can acidify the blood, so you kind of want to keep that out of the blood, so that kind of helps keep things out of the blood that you don't want to let in, but while still allowing efficient gas exchange. It's just that the gaps between the endothelial cells are very slender, so you're limiting what's being exchanged, just small molecules. Limits exchange to small molecules. Like water, oxygen, CO2, glucose. Then you have fenestrated capillaries, which are more leaky. Fenestration is a hole. The ECs have holes, and you start to see gaps between the ECs. Remember, ECs are the endothelial cells. They have fenestrations, or holes, so that allows for more exchange. And you have gaps between the ECs. ECs have gaps / clefts between them. Which allows for more exchange. You usually see this type of capillary bed in intestines, in kidney. Small intestine. These are organs where you want to allow larger molecules to pass through. Like, for example, in the small intestine, the products of digestion, right? Larger food molecules can get in there. Kidney filters all the blood plasma, so you want to allow more filtration there. So if you notice, they do speckle the ECs with little holes called fenestrations. And you can't see the gaps on this slide very well, but the next slide will show it. This third category, very leaky, are called sinusoidal capillaries. The fenestrations and gaps are so large, whole cells can enter or exit the blood. Gaps, fenestrations. Are so large. Whole cells can cross. The capillary wall. Well, where you want to do that, for example, in the bone marrow. Bone marrow, well, the red marrow. You have red marrow in your cranial bones, in your sternum, in your iliac bone. This is the tissue that produces all the blood cells. So if you're producing blood cells, those blood cells have to enter the bloodstream. So you need this kind of capillary to get in. Or another example, lymphatics, like for example, lymph node. Sometimes you deposit lymphocytes in the lymph node. So the lymphocytes develop in, for example, the thymus, the T cells. And they have to like enter a lymph node. They kind of have to enter and exit sinusoidal capillaries. Anyways, I think the idea that they're leaky to some extent is pretty easy to understand. If you kind of look at this illustration, they got holes in them, right? But they got gaps in between the cells too, so things can pass easily through the basement membrane. I think the real picture is much better. Okay, it's funny, they switch the lights from that room to this room, so I always have to like relearn it. And they switch from room to room. Anyways, you're looking at the inside of a kidney capillary called the glomerulus. And they point to like, well anyways, do you see all the little speckled holes? There's so many fenestrations. So I think that's pretty remarkable to see there. Let's go back to the histology pictures that I took pictures of. This one is showing a capillary wall. Again, how did I know? I saw this. That's one red blood cell, and do you see how it occupies the entire diameter? Oh, so that's by definition capillaries. And I looked for the layers, and I only saw one, just TI. Okay, that's the clues that you need to use to identify a capillary. So all the blood from the capillaries has to be collected by veins. Let's go through them. So we'll start with the smallest veins, which reform into larger veins, which all reform into the vena cava. The smallest veins after capillaries are venules. Up to 2 layers now. Again, TI, TM, no TA. So look at the picture of a venule. I see the TI, the endothelium. Identify cell. That one. They show you a few spindle-shaped cells. These are the smooth muscle cells. What layer is the smooth muscle cells? TM. TM. So that's how they draw it. You know, the venules, they're capillary-like. They're able to pick up a lot of things that have been exchanged. They're almost capillaries themselves. You're just starting to add smooth muscle cells. So we call them venules. They reform into like larger veins. When I say reform, I mean like a small venule. Maybe it kind of like reforms into this larger vessel. And maybe these 2 large vessels will reform into this larger vessel. So blood is flowing into larger and larger tributaries. Small tributaries funnel into larger tributaries. This is how the veins work. You're collecting blood from the smallest veins called venules, and you're reforming into larger veins. So they literally call them small veins and large veins, although not on this figure. Okay. So you go from venule to say small vein, or large vein, I guess. You're back to 3 layers. All right, all 3 did. That's how they illustrate it. TI, TM, TA. Usually on the large veins, the TA is most prominent, the large veins. The veins will collect the blood and return it to the heart. So that's why for this vein, they put fibrous collagenous tissue as the biggest bar, because that is mostly what you have in the TA. Back to 3 layers to reform. Let's look at the veins. In the liver, well, how livers work is they're arranged in lobes, liver lobule, and all the hepatocytes, think of the central vein as a shower drain. Like when you shower, all the water's on the base, and then it all funnels towards the drain. Blood is flowing in from each corners of this hexagon towards the central vein. And as blood in the sinusoids flows towards the middle, the hepatocytes do their job. The blood has been received from the digestive tract mostly. We'll get to that. But anyways, once it gets to the vein, it's on the way out. So that vessel in the middle is categorized as a venule. It's the only venule I could think of that I have access to in our collection. This next picture we looked at before, right? Large vein. Can you identify the 3 layers? Well, let's see. Where's my arrows? There's one. My other arrows. Wait, let me just point to them. I don't have my arrows. If I point to the innermost layer, what am I going for? TI. See this pink from there to there? TM, and then from here with the black and the red, TA. Okay. Large veins have all 3 layers. Here they are labeled more clearly. TI, TM, TA. Okay, well anyways, those are the histological properties of veins. What talked about the capillaries, I didn't talk about the physiology of exchange. Okay, I just categorized the different types of capillaries, but you have to know the physiology behind the capillary exchange, so I gotta cover that now. So there's some things I need to define that may not be apparent to you.
I have a quick question.
Sure, go ahead.
I missed the part where you said, so are venules, what's the connection between venules and veins? Or
Yeah, venules are the smallest veins.
the smallest veins? Okay.
Yeah, and they'll merge and merge to form small veins. Small veins will merge and merge to form large veins. That's all I'm saying. You're welcome. And going back to capillaries, okay, so we have fluid compartments. You're exchanging blood from inside the capillary, called the plasma, that's the liquid part of the blood, with the fluid outside the capillary, the interstitial fluid. So exchange happens there. Of course, you have fluid inside the cell too. We have these different kinds of pressures. Let me start by defining these. Hydrostatic pressure. Think of hydrostatic pressure as blood pressure. I mean, this is it's a pressure that, in terms of capillary exchange, it'll force fluids out. Okay, but that's force. Pressure is a force. Force fluids out. You know, when I use force in a science class, I'm thinking of physics, like force equals mass times acceleration, but not like Star Wars force, but force. You force fluids out. I don't mean it as in a metaphorical sense, okay? Pressure is a force that you can learn about in physics. And here, let's just, very simply, normally, when blood flows through a tube, we want the blood vessel to keep all the blood inside. We don't want it to leak. It's got pressure, it's pushing against the vessel wall, but we don't want it to leak. If it does, that's called hemorrhage and bleeding. We don't like that. But by capillaries, when you get to capillaries, smaller vessels, you know, we want it to you want to force those fluids out. We want there to be exchange. So fluid exchange is one of the things that happens. Hydrostatic pressure will push that fluid out. It's like if you have a garden hose and you poke holes along the garden holes, like with a pin or something. I mean, the water would squirt out, right? That's the force I'm talking about. That hydrostatic force pushes the fluids out. The opposite, the opposing force, is colloid osmotic pressure. That helps the blood vessel retain fluids. Okay, so it opposes hydrostatic pressure. It keeps fluids in the blood vessel. I just think of it as there's stuff, quote unquote, in the blood, and that stuff keeps water with the blood. It doesn't allow it to leave, okay? We always teach that rule when we teach osmosis. Or at least I teach the rule. I call it the golden rule of biology. Water goes to where the most stuff is. That's osmosis, the diffusion of water. So if you have more stuff in the blood, like albumin, red blood cells, your crit. Crit is short for hematocrit, which is the estimation of your red blood cell count. Stuff that keeps fluids in there, it's opposing hydrostatic pressure. It's like a sucking pressure. Like pressure, fluids are drawn into you with high colloid osmotic pressure. So the word osmotic is used because it's referring to osmosis. Fluids enter the blood vessel or are kept in the blood vessel. Colloid is used because blood is considered a colloid suspension. What's that? I took chemistry, look in your chemistry book, what a colloid suspension is. It's like the plasma and the crit, and they're all mixed up, but they can separate, you know. But anyways, blood is considered a colloid suspension. This pressure keeps fluids in the blood. Any question? This pressure is kind of weird. This is usually what I think of when I think of pressure. This is a sucking pressure. For example, if you have high blood pressure, doesn't the doctor want to lower your blood pressure? And what kind of diet do they prescribe? High or low sodium? Low. Why? What's sodium? Sodium is stuff that would keep fluid in your blood and keep your blood pressure high. So a low sodium diet will help relieve some of this pressure to lower your blood pressure. But don't you get thirsty when you eat pizza? It's all that sodium, you just drink water. Well, anyways, that is the two pressures that oppose each other in capillary exchange. So the terms that are used, you force fluid out of the capillary, filtration, fluid into the capillary, absorption. Versus here, absorption. It's just a matter of which pressure is greater in the capillary. That will determine how fluids flow in or out. Net flow in, net flow out. Other exchange things that happen are based upon diffusion. So we have filtration versus absorption. You also have diffusion going on. Molecules flow down their diffusion gradients. Oh, concentration gradients. Via diffusion. Molecules flow down the concentration gradients via diffusion. That's what I'm writing. Now we teach diffusion in 431, so I don't have to reteach that. I mean, basically it's you flow from an area of high concentration to low concentration. So for example, oxygen, if the blood is oxygenated and it gets to the capillary, it'll leave the capillary because the tissues are hypoxic. They don't have as much oxygen. So, and the same thing for nutrients like glucose. It'll flow out of the blood, and it's good to kind of visualize one capillary to kind of talk about this. So there's a lot of things going on here. Let me define what you should be looking at. One end of the capillary is on the arterial side. It's the red end. If you look at the hydrostatic pressure, they label it P cap. So P cap is hydrostatic pressure. and pi cap, I don't know why they use the simple pi, but that's the other one. That's the colloid osmotic pressure thing. Sometimes it's called oncotic pressure. That term is also used. I tend to use blood colloid osmotic pressure. Well, anyways, in the arterial end, the P cap is 32 millimeters of mercury. I'll tell you where I got that from. It's right here. It's probably hard to see that number right there. The pi cap is negative 25. Now, it's not negative, really. It's the force is in the opposite direction. So they put a negative sign because it's opposite. It's 25. It's negative 25. So what's the difference? 7. Which force is greater? The hydrostatic pressure. You have net flow out. Net fluids out. That's what they illustrate. The arrows are going out. So the down arrows are the red arrows. Notice the blood colloid osmotic pressure stays pretty consistent, negative 25 to negative 25 from end to end. It's the hydrostatic pressure that's dropping because you're losing fluid as you travel along the length of the capillary. Okay? So basically, P cap is greater than the pi cap. That's why you have net fluids out. But you also have oxygen that leaves, O2, nutrients diffuse out. That's all the things I want you to know at the arterial end. That's pretty much the good stuff, right? That's what the capillary is supposed to do right here. Deliver the goods. At the midsection, well, it's not quite the midsection, but the point where pi cap equals, the point where P cap equals pi cap, where the hydrostatic equals the osmotic pressure, there's no net fluid flow in or out. No net flow in or out because the forces are equal. So nothing's diffusing in or out either. So nothing's happening there. The capillary midsection on the figure is where the forces cross, right here at this singular point, right around there, okay? So at the other end, the venous end, you have net absorption going on. Here you had net flows out. We call that filtration. On the venous end, the hydrostatic pressure, P cap, is less than colloid osmotic pressure, the pi cap, so you have net absorption. This is also where CO2 and other metabolic waste products enter the venous blood, so the body can process it. Like your filter organs, the spleen, the liver. So CO2 is considered a metabolic waste product. Other metabolic waste products are like nitrogenous waste products. I'll just say they enter at the venous end. You get net fluid absorption too. So one other thing to notice that ties back to lymphatics. Notice there's more fluid out than fluid in. There's net flow 2 liters a day. Lymphatics picks that up. The failure of lymphatics would lead to swelling. Now the figures in your book aren't like that one, but they're nice to look at. They show you the fluid exchange at the different parts of the capillary bed. But we've already noted what you're supposed to know about that. Well, anyways, the forces are greater here, the hydrostatic pressure forces are greater, so you have net fluids out, no fluid exchange. But here, the little black arrows are pointed in, net absorption, and you have lymphatics here picking up some of the fluids. And don't forget about the other things that are exchanged. The metabolic exchange. O2 nutrients diffuse out, CO2 and waste diffuse in. That's basically it. The other thing about capillary exchange that's shown here is that they have the most cross-sectional area. So this is an inverse curve to that one. So let's kind of explore what's going on there. Here's a way to put it in like a quiz or test question form. Which vessels have the most cross-sectional area? cm squared. Cross-sectional area. And you're supposed to look at the x-axis, I guess, and deduce that it's capillaries, right? Capillaries have the most cross-sectional area. Even though they're the smallest individually, there's so many of them, you add it all up, they have the most area. So it's kind of, you know, the smallest ones have the most area, if you can remember that. Another one is, well, which vessels have the slowest velocity of blood flow? Answer for this one and this one, both capillaries. The idea of fluid flow is studied in physics, and for blood flow in this class, the idea is pretty simple. The idea is, I don't know if I want to try to draw that. I'm not going to try to draw it. I was going to draw this. It's like, I use the analogy of whitewater rapids. I haven't really gone in years, but it's fun, right? You go whitewater rapids because you're just bumping all over the place. Your friend falls out of the boat and everybody laughs. But anyways, it's fun because it's fast and it's turbulent. That's how blood flow is here, okay? Now, when the water has more area to flow in, it's like if the whitewater rapids, you hit that wide expanse, what happens to your raft? Everything slows down and it's calm, right? It's kind of like this. When you get to the capillaries, it's like hitting that wide expanse. Everything slows down because there's more area for the fluid to flow, okay? So that's why capillaries have the slowest velocity of blood flow, and that's good for exchange. It allows time for exchange. Moving on. So I talked about the blood pressure of the arteries, but I didn't talk about the details. So to make sure you know the details, I call them basics. What is blood flow? What is blood pressure? To strictly define it, there's actually 3 kinds. And the resistance to blood flow. And this is my easiest way to outline a complex topic: blood flow, blood pressure, and resistance to blood flow. And I want to talk about the mean arterial pressure, because that is the main thing keeping us alive. It's our body's ability to control this. MAP is controlled, is maintained by controlling the blood the inflow and the outflow. Okay, so you maintain blood pressure by controlling the inflow and the outflow. Now, we've used these terms before for the cardiac cycle. You had inflow into the ventricles, you had outflow of the ventricles. But now we're talking about the systemic arteries, the inflow and the outflow of systemic arteries. Okay, so this is the picture I usually use to teach that. So changing gears. The first part of the lecture is more vessel structure, but this is more blood pressure physiology than the first half of the lecture here. So what I tried to say on that first slide, blood pressure can be expressed as one number, the mean arterial pressure, right? I taught you how to calculate that. 93 millimeters of mercury. It's maintained by controlling inflow, outflow. Inflow and outflow of systemic arteries. So that's why I put this diagram in there. Because for us, we're talking about arteries, inflow is determined by the cardiac output, right? And we know that cardiac output is the heart rate times the stroke volume. We just had a test on that. So we're going to look at heart rate and stroke volume. As long as your cardiac output is adequate, you should have enough blood pressure. But of course, you have to look at the other end. In our discussion of blood vessels, in terms of arteries, what are the last, smallest arteries called before the capillaries? The two layers. Arterioles. So that kind of represents that. So the outflow is kind of like the peripheral resistance provided mostly by arterioles, right? Because you can control how much blood is in the tube by controlling that as well as that. Controlled by peripheral resistance. And in this lecture, I usually use a PR or an R to symbolize resistance, controlled by the peripheral resistance provided by arterioles. That's the outflow. Okay, we call that outflow. So let me see if you're with me here. So what if inflow goes up and outflow goes down? What's going to happen to the pressure? What pressure will you observe? How will that change? Will that go up or down? If this is what occurs. Increase the inflow, decrease the outflow. Well, you should increase the blood pressure. That's the relationship I want you to see right now. I'll get into the details. Increase the cardiac output, squeeze here, you're keeping more blood in the arterial side. That'll help keep the blood pressure up, say during a sympathetic response, keep blood flow into the vital organs. And so what if you did the inverse? For whatever reason, the heart shutting down, decrease the inflow, you're letting the blood leak out, pressure will drop. That might lead to shock, so something's wrong, obviously. You don't want to allow that to happen, but this is how we're controlling the blood pressure in the arteries. It's maintained by controlling what's going in and what's coming out. because the artery is already a stiff vessel, and it's already pretty much at full capacity, so you really can't change that. You can just control letting the blood out, letting the blood in. So that's why they have this CVP thing here, and you already know that. Let me prove to you that you know that. So let's just talk about this conceptually. The C is capacitance, the volume and pressure. Okay, let's say arteries. Arteries, do they hold a large volume or a small volume? Small volume. So picture a small number in the numerator. What pressures did we observe in them? High pressures. Let's see. Yeah, this is right. C. So what happens when you divide a small number by a large number? You get a small number. That's why we say arteries are small capacitance. We said that already. So let's do the same thing for veins. What volume of blood do they hold, large or small? Veins held most of your blood. So put a large number in the numerator. And what pressures did we observe? Small. So if you divide a large number by a small number, you get a very large number. That's why we said veins are large capacitance. So, you know, we're not going to plug numbers in, but that's why they have that there. That's why they draw this bigger than this. The venous side is bigger, it's the blood reservoir. I kind of like that illustration. So the book talks about, it uses the term flow, like in a physics class when you study the properties of liquids and how they flow. So for us, I could just use cardiac output, because that's establishing the blood flow for the circulatory system. In any generic class when you're studying fluid flow and fluid mechanics, the flow of any fluid, you study it by talking about flow past a fixed point. That kind of gives you your flow rate, so you can assess that. So for us, it's simply blood flow past the semilunar valve. That's what we got to think about. So blood flow, or F for flow, is really cardiac output. And we know that cardiac output is a product of heart rate times stroke volume. And these terms are what I usually talk about most in a physiology class, because those are the things that the body can modify. To modify the cardiac output, to modify the inflow. Okay, so that's pretty much blood flow for this class. It's established by cardiac output. Okay, and that's our inflow. That's the job of the heart, pumping blood into the aorta. So once you accomplish that, you can talk about the pressure inside the arteries themselves, the blood pressure. Because the blood exerts a force or pressure on the vessel wall, which can be measured in a variety of ways. And I use this figure to help me teach those three terms on the top there. So let's define different kinds of blood pressure. When you talk about blood pressure, you always talk about a pressure gradient, because you're talking about a system where blood flows. Blood goes round and round. It keeps flowing in a circuit. So it's always a pressure gradient. Okay, from high to low. And, well, okay, so let me get into this here. So they kind of like give you an example of a leg at an angle. Maybe some of you are sitting like this at this angle now, and there's an artery or the blood vessel in there, And if you free body diagram it, basically you get the difference between this point and this point, call it delta x. Delta means change. In the vertical plane, delta h, and you even consider across the vessel wall, call it R1, R2, delta R. So let me start with the delta H between those 2 points. So when you have a gradient, it's always like high to low. Okay, it's always 2 points. Blood pressure is always a pressure gradient, I should add on, between 2 points. So the delta H is supposed to be hydrostatic pressure. I'll just define it as the pressure against gravity, okay? Because we are upright, and the heart's in your chest. So for example, to get blood to your head, you have to pump against gravity. So that's something to be considered. And that's all I'll say about that. I don't talk about it too much more than that. The transmural pressure is the delta R. A mural is something you hang on the wall. So transmural means the pressure difference across the vessel wall. This pressure is important to teach because it's the one your body can detect. Your body monitors blood pressure, and if it drops, it wants to raise it. Let's see if this will work. Imagine you have a nerve ending inside the vessel wall. Sensory neuron, let's go to the CNS. Okay, if you live inside the vessel wall, you can detect a change in pressure across the vessel wall. Okay, so if pressure is really increasing, I mean, we'll learn that this is called like the baroreceptor word. That's basically tomorrow's lecture. You can detect that change. If pressure is dropping inside here, you'd feel it inside the wall. You'd stretch it more or stretch it less, depending upon what's going on with the pressure inside. So this is the one your body can detect. It's the baroreceptor. The baroreceptor reflex is tomorrow's lab, and I left that lab over there by the door. If you didn't get one, be sure to pick one up or it's on campus. And while I'm thinking about it, tomorrow's lab, if you read through it, it'll require you to get in groups again. It's one of my mandatory labs, and I would suggest that you have to lie on the ground again, your subject does. Maybe this time you can plan ahead and bring a yoga mat or something, if last time what you arranged was not comfortable. So you could talk about that after class. But anyways, baroreceptor lab tomorrow, the baroreceptor reflex. This is why transmural pressure is important. You can detect it. All right, that third pressure, the delta X, it's along the central axis of the blood vessel. We call it the driving pressure. This is the important one. The driving pressure is by definition along the central axis of the vessel. So this is the pressure that's actually the one you measure on your patient. It's the one that's keeping blood driving from arteries to capillaries. Okay. So when you measure BP in your subject tomorrow, So this is the one you measure in the patient. It's the pressure of the vessel that keeps the blood flowing. So I have another slide on it. Think of it as flow between 2 points along the tube. It's right along the central axis. So it depends on a change in pressure. Blood flow depends on a change in pressure, right? Not what we call absolute pressure. So driving pressure depends on delta P change, not absolute P. Write that down. Depends on a change in pressure. So what did I calculate mean arterial pressure to be? 93. Let's just put 93 here. Capillary pressure is usually around 30. That's enough of a difference to drive pressure from high to low. What if you spring a leak, you're hemorrhaging, and the 93 drops? 83, 73, 63. What's happening to my gradient from high to low? I'm losing it. So what's going to happen to blood flow when you start to lose pressure? It's going to stop circulating, and that can lead to shock. This is why we're trying to keep blood pressure high, normal, in your patient. That's the driving pressure. So to illustrate that point here, I have 2 tubes. Assume everything's equal, A and B. Read the question. Which one would you choose? Talk about it with your neighbor. I'll give you half a minute. The answer is the one with the steeper gradient. The difference between the points in A is like 80. What's the difference here? 25. A will have a higher flow rate. That's what physics tells us about fluid flow. Okay. Students might think, but that's a higher number. But what's the number? You know, it's harder to flow when the pressure here is higher. So basically, so let me ask and answer this question. Which cardiovascular structure generates the pressure? It's the left ventricle. It's giving us the pressure we need in the artery. Okay. All right, so peripheral resistance. I think we teach this, and I'll stop after this. So as I'm erasing this, was peripheral resistance the inflow or the outflow? It was the outflow. So that's what I'm talking about now. Right here. Sometimes I drop the peripheral, I'll just call it resistance, capital R. This controls the outflow of blood. So if determinants, well basically anything that resists blood flowing is categorized as resistance. The major source of resistance is actually friction. Friction of the blood rubbing against the inside of the blood vessel. But I have these other determinants besides friction. For example, blood viscosity. So blood viscosity is the goopiness of blood. For example, water is less viscous than, say, maple syrup. Okay, so blood is somewhere in between there. And For adults, the blood viscosity is largely determined by the hematocrit, which stays relatively constant. So in adults, this is pretty much a constant. And I don't really mention it in this class, other than it's considered. Blood vessel length. The length of the vessel, well, for example, all things being equal, if you have a vessel that's, say, twice as long, a longer vessel provides more resistance simply because it's longer and there's more friction. But in adults, the length of your blood vessels really doesn't change, so this is a constant. I don't really talk about it. Turbulent blood flow. Turbulence is a source of resistance, but it's going to happen because mostly it's created by when you have a fork in the road, when arteries bifurcate. That bifurcation kind of creates, well, what's called turbulence. Okay, the opposite of turbulence is laminar. Put that in parentheses. Laminar is the blood is flowing smoothly in neat, defined layers. And, well, the goal is laminar blood flow, but you have turbulence as a source of peripheral resistance. But I don't really talk about this one much either. It's really the last one that's important to understand. It's not hard to understand. Vasoconstriction. You can physiologically vasoconstrict vessels or dilate them, and you control the radius. That is the strongest determinant of peripheral resistance. Vessel radius, symbolized by lowercase r, not to be confused with uppercase R for overall resistance. In fact, this vessel radius affects resistance so much, it's inversely related to peripheral resistance to the fourth power. So basically, here's how you see it in your book mathematically. The fourth power simply means it affects it a lot. You decrease the radius a little bit, you increase the resistance a lot. Think of it that way, to the fourth power. So, for example, if this is your blood vessel, you have blood flowing nicely, but you squeeze in one location. Right there where you're squeezing, that's what I'm talking about. That's vasoconstriction. Where blood flow, you would have a remarkable increase in resistance to blood flow. Decrease lowercase r, decrease the radius for blood to flow. Increase overall peripheral resistance. That's kind of the relationship we want students to know. When you vasoconstrict, VC, you basically increase blood pressure in the arteries, BP. That's the basic relationship I want you to know. So the opposite is VD, vasodilation, open it up. You vasodilate, you let more blood out, that should drop the blood pressure. I think we can stop here. I'll pick it up here tomorrow. I want to end a little early because I have your repro essays. If you wanted to see that, you can stay after class. If not, you're excused. I'll see you tomorrow.